So we're going to talk about another tangent line approximation, and it's called Eulers' method. And what I want you to know about this is actually a pretty super important AP topic. You're often going to see this paired with differential equations, so pretty important that you kind of understand this concept. I want you to know that this is pretty similar to Newton's method of approximating zeros. And really, to explain this, we're going to explain this through an example. So the first thing it says is I've got a differential equation, and where you're going to see this concept tested is then a differential equation problem. It's appeared in several free response questions paired with a differential equation. It says let y equals f of x be a particular solution to the given differential equation with an initial condition. Now guys, this differential equation is not separable. You can't subtract y, you can't solve this. So you've got an initial condition and you cannot separate it and solve it. So if I were to graph this initial condition, this 1, 2, 3, 4, -1. And I could take my differential equation and I could build a tangent line there. So imagine for a second, let's zoom in. So here is 4, here's this point, and I build a super tiny tangent line right there, okay? And then I go build another tangent line a short step away and do that. And then I go build another tangent line a tiny step away. If I keep building successive tangent lines, I should be able to come up with an approximation for where my point will fall, or the next point, okay? An approximation for my function. So it says we're going to start at x equals 4 with 2 steps of equal size, and I want to get to f of 4.2. Now guys, you have no way of knowing what the original function f is because again, you have not separated and solved this equation. So let's start simple. If my initial point is 4, -1, and I want to go from 4 to 4.2 in tiny steps, and it tells me 2 steps in the problem, then we're going to have a delta x equal to 0.1. We'll go from 4 to 4.1 to 4.2 and take 2 steps, okay? What we're going to be doing is using tangent lines at 4 and 4.1 to project a distance of delta x equals 0.1. So this width right here is 0.1, okay? Now I'm going to go ahead and throw the formula at you, and we're not going to go through the big process of deriving this formula, and I'm going to show you a couple of versions. So in calculus books, you're going to see y sub n plus 1 is equal to y sub n plus delta x times capital F of x, comma, y. What in the heck does this mean? This is called next y, previous y, delta x is change in x, and f comma xy is your differential equation, also known as y prime. Okay, so that's one version of the formula, but this formula has also been shown as y sub n plus 1 is equal to y sub n plus delta x times dy dx. This is the version that I want you to know and remember. Okay, so this is the one. Now, why does this work? the reason this works is because if you think about dy dx as delta y over delta x times this plus y sub n, what's really going to happen is my delta x's are going to cancel out, and it really is just saying y sub n plus 1 is equal to the previous y plus the change in y, because what we're interested in finding is y values, okay? So this guy right here, we're finding y values on our function, and we're making projections of tiny, tiny tangent lines, okay? Now the way that I set up my problem, every single time I do one of these, is I always start off with my initial point. So we have the initial point for -1, okay? Now, in order for us to find our next y, keep in mind we wanted to go from 4 to 4.1 to 4.2. So that is kind of our path that we're planning to take here, okay? So if I want to find f of 4.1, okay, according to my formula, I want to take my previous y value, which is -1, plus delta x, which earlier we said delta x was 0.1, and I'm going to multiply it by dy dx. Now, let me go ahead and remind you that the given dy dx from the problem was x plus y. So I'm going to plug in x plus y, the previous x value and the previous y value. So nowhere am I using 4.1 in this equation. I am using the point we're starting at, okay? So previous y value, my delta x, and then x plus y, which was the differential equation, okay? And so what I get is -1 plus 0.1 times 4 minus 1 should give me a value of about -0.7. So what this means is f of 4.1 is approximately -0.7. So what we've just done is we've taken one step. This is one step, and I'm now at a new point. My new point, that's a terrible color, is 4.1 comma -0.7. And so this is the point I'm going to use in all of my calculations. And if I want to find f of 4.2 and take my second step, we're going to be using an approximation coming from this point. So I'm going to take my previous y value plus delta x times the derivative using the point that I'm coming from. So x plus y. Now, the number one mistake that students make when they're doing these kinds of problems is that they try and use 4.2 in this equation. Notice that I am not using 4.2 at all in my computation. I'm using the y value and the x value of the point that we're projecting from. And so now I get a value of about -0.36, and I've achieved my goal. I've taken my second step, and I have figured out that f of 4.2 is approximately -0.36. And what we've effectively done is we started at this point for -1, and we made a tiny tangent line and projected forward. And then we made another tangent line, and then we made another tangent line, and we got an approximation for where this function value could be close to. And the reason we need that is because this is a non-solvable differential equation. Okay? So what I want to do next is look at some styles of AP questions for this, because this is a pretty easy concept. So what is it going to look like on the AP exam? And I've got, I think, 3 examples we're going to run through. Okay? I'll probably do 2 of them with you and then let you guys try one. Be very attentive to how I'm setting up these questions because this is exactly the process that's going to help you organize your material. So you're always going to get a differential equation in an Eulers method question. You're always going to get an initial condition, and they'll ask you to find a value, either telling you how many steps to take or specifying the step size. So in this question, we know we're going to start at 1, -2. I want to end up at 1.4. We're taking 2 steps. And so if I want to end up at 1.4, my 2 steps, I'm going to go from 1 to 1.2 to 1.4. So delta x, even though not given in the problem, is 0.2. Really important that you figure that out. Okay? Now I'm going to write my formula because I think it's a pretty important thing to know. To find the next y value, I take the previous y value, delta x times dy dx. Now when you say dy dx, I want you always thinking dy dx from the previous point. So we're going to put our previous point. Our starting point is 1, -2. Okay? And so I want to use this point to predict what f of the next point is going to be. So I'm going to take my previous y value plus delta x times dy dx. Now remember, dy dx is up here. So x minus y minus 1. So -2 plus 0.2 times 1 plus 2 minus 1 should be approximately -1.6. I like to draw a line because that is one step, and I like to write my next point. My next point is 1.2 comma -1.6. Guys, the math on this isn't hard. It's remembering how to set up the problem and to structure it in a way that you don't get lost in your work. So now I want to find f of 1.4 because that's what the problem asked me to find, f of 1.4. So we're going to use this previous point, this previous x and y value to find my next point. So I'm going to take my previous y plus my delta x times the derivative using the previous point. So x minus y minus 1. And I get a value of about -1.24. So therefore I can say that f of 1.4 is approximately -1.24 or here. So kind of my friendly reminder is every single time you are using this point, you're using this point, nowhere will you actually use the 1.2 or the 1.4 for the current calculation. Now, I like this next question because it's a table format, and this is very, very AP style, and I know it's blurry on my screen and a little bit blurry in your notes, but that's just kind of how it photocopied. So it says, the table below gives derivatives f prime of a function. Notice you've once again been given an initial point, and I want to approximate f of 2 using Eulers' method, and they've indicated the step size. So we're starting at 1.4. We've been given delta x is 0.5, and we want to end up at 2, okay? So let's write our formula, just good habit. Y sub n plus 1 is equal to y sub n plus delta x times dy dx, okay? My initial point, we're starting with 1.4. If I take a step 0.5 units out, I'm going to be finding f of 1.5, okay? So we're going to plug in our previous y value plus delta x times dy dx. Here's where you're going to mess up, guys. I want the dy dx for this point. So that dy dx point, okay? Now remember the dy dx is f prime. Those are the same thing. Derivative is f prime. So I want the derivative 0.2 from the table, that is dy dx for x equals 1. Notice I didn't take the dy dx for 1.5. I took the dy dx for 1 because we're only using this point in this calculation. So when all is said and done, I should end up with an answer here of 4.1. You've now taken one step and we're at a new point. Our new point is 1.5, comma, 4.1. And if I take a step half a unit out, or 0.5 out, I'm at f of 2. So we're going to be using 1.5 and 4.1 to calculate f of 2. So I take my previous y value plus delta x times dy dx, dy dx for the previous point. So I want the dy dx for x equals 1.5. So I'm going to put 0.5 in here and get a value of 4.35. I guarantee you the mistake you're going to make is you're going to think that in this Eulers table you'll have to use that 0.9 and you don't at all. Okay? So be really, really careful with that. I've got one for you guys to try. It gives you a differential equation. It gives you an initial condition. It tells you 2 steps, and you're going to end up at f of 2. So maybe give this one a try and see how it goes. And that's pretty much it.